All right, trying again, Kelsey. Here we go. All right. We circled the given. They denote the given like in this fashion right here. They put a line right here for the given. Okay, that line is kind of a handy thing because that is the line of where our bar goes. Okay, we're creating a fraction. We have some top stuff, we have some bottom stuff. This is something called a conditional probability. Okay, so what we normally do for a probability is we put the total number down here, right? Total. So like out of this class, I would normally put 14 as that bottom number, right? There's 14 in this class. But if I say given we know that the person I'm selecting is a girl, now that number goes from 14 down to 10, okay? So this is a condition. Under the condition that we know that we're selecting a girl, that changes my new bottom number, right? So your given is your bottom number. That what we're looking at or what we're given is going to change what my bottom number is, all right? So we are given the subject uses drugs. So out of this table, who uses drugs?
Me. 50.
There are 50 people that uses drugs, right? These 50 across here. Let me circle. 50 across here uses drugs, regardless of how they test. There are 50 people that use drugs. That is my bottom number. Now, of those, who tested positive? 45, right? So we're not talking about all 555 test subjects. We're only talking about the given people, and then of those, who falls into this category. So 45 out of 50, or 9 over 10, or 90%, however they ask you to write the answer. All right, next one. This one, I'm just going to go down to the notation. Given, so subject uses drugs given that they had a positive test. So we're looking at the given. Given positive test. Who are my positive testers? Given positive test.
45. No, plus 25.
Positive testers, regardless of whether they use or don't use. There is 70. Okay, so 70 is my bottom number. Of those positive testers, who uses drugs? Uses drugs would be the yes. So 45 out of 70. If I reduce, that would be 9 out of 14. 9 out of 14, I believe. Or whatever decimal they want, okay? So the given part is going to designate your new bottom number. It's like you're reading this backwards, okay? 64.2%, perfect. They're going to probably ask you for the 3 decimal places, so it'd be like 0.642, whatever. Anyway, okay, good? All right, confusion of the inverse. Here we go. They say right here, the probability of B given that A has happened is not the same thing as the probability of A given B has happened. Make sense?
Yeah.
Okay, let's do an example in here. Let's do probability of blue eyes given girl. And then we'll do probability of girl given blue eyes. So I need your help here. Who are we missing? Kelsey? What color eyes does Kelsey have?
Blue.
Kelsey has blue? Okay, we'll say Kelsey. Kelsey, I don't know if you have blue or not, but they say blue. Okay, so blue given girl. All right, blue given girl. My girl is my bottom number. How many girls do we have in this room, including Kelsey?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10 girls. Of those 10 girls. Of those 10 girls, right? There's 4 boys, so there's 10 girls because there's 14 together. We're including Kelsey. We're pretending that she is here. So, given girl, we have 10 girls out of this room. How many of those 10 girls have blue eyes? Raise your hand. Blue eyes. You're blue? You're not blue. You're not blue. Blue. So that's 2. 3, 4, 5 is Kelsey. Are you blue? Okay. So 5 out of 10 or 1/2 is my probability of getting a blue-eyed person given that they're a girl. We're not talking about all 14 anymore. We're only talking about the girls. All right, now let's do it the other way around. This one is given blue eyes. Okay, how many blue-eyed people do we have in here? 5 boys. Are you blue?
I'm actually feeling pretty.
No.
Are you blue? You're
No,
blue?
you're not even
So that would
No,
be a
I'm
6th blue?
I have heterochromia.
And no one
Okay,
if
tell me,
it's
are you blue or not blue?
No.
No. Clayton, are you blue?
No.
No. Marcus, are you blue?
He's a green.
Yes, Marcus is blue. Are you blue?
He's a green. You're
So
a
we've
brown.
got 6 blue-eyed people. We're going blue-eyed people first. Of those 6, how many are girls? Of those 6 blue-eyed people, how many are girls? 5 out of 6. These 2 do not match. So blue given girl is not the same thing as girl given blue. That's what they're saying. They're saying the confusion of the inverse. If you switch them around, it is not correct. So you have to be, like, make sure you do the given part right. Good? Okay, let's talk about this one.
Leonardo.
This one's kind of interesting. Here we go. Event, you gotta listen. Event D is it being dark outside, okay? So like right now it's dark from how much? 8 o'clock to 6. We'll say 8 p.m. to 6 in the morning, whatever, right? That's when it's dark. The second event is that it's midnight. Okay, so we want to know the probability of it being dark given that it's midnight. So given that it's midnight, what's the chances that it's dark outside? If we know that it is midnight out right now, what's the chances that it's dark out?
Yeah, 100.
100%, right? In the area that we live, right? It says it's certain, this is excluding, it says we conveniently ignore the Alaskan winter and such anomalies. So that means like in Alaska where it's like light 23 hours of the day, whatever. Okay, so the probability of being dark given that it's midnight is 100%. Okay, what's the probability that it is midnight given that it's dark? So I'm talking about dark hours, any dark hour. What's the chances of it hitting midnight exactly? I'm picking any dark hour. Any dark hour. So I'm like 3:01 in the morning. That's a dark hour. Any dark hour or any dark time, right? What's the chances of me choosing midnight
Not
exactly?
a lot.
Probably, they call it 0+, which means like really, really close to, like slim to none, is the chances of me hitting midnight on the nose, right? Okay, if I'm choosing any dark hour. So those two things are not the same, all right? Okay, let's go down to this example. We have to draw a table,
No.
okay? They give me this table. Let's talk about what the table is doing first, and then we'll fill the data in. Okay, so we're talking about a positive test versus a negative test, and then we talk about cancer or no cancer, okay? So let's see who my false positives are. Where does the false positive live?
No cancer.
False positive.
Cancer.
Out of
no
these four.
Negative.
Out of these four.
Right there. No, that right there.
False positives. Bottom left. This is a false positive, okay? Those people are testing positive even though they are no cancer. This is like the J.C. Himmelbergs. Do you guys remember that
Yes.
when he was in 7th grade? Okay, I talk about that all the time. False positive, okay? False negatives. False negatives would have cancer but be negative. Now, if you had to be one of the two, which one would you rather be?
False positive.
You would rather be a false positive. You would rather have the crap scared out of you and like actually end up being no cancer. I agree. I would rather be a false positive because what happens to the false negative people?
They don't get treatment.
They don't get treatment, and then like 2 weeks later they're like done, right? That stinks, right? So that's how this table is breaking down. All right, they're going to give me some data, and they said the probability of cancer. You got to listen. The probability of cancer is 1%, okay? I always start down here in the bottom corner with a really, really big number, okay? I start with like 100,000. So we're making these numbers up just as long as they correspond to the percentages they give me, okay? You're going to fill every single table out to look like this. I always start with 100,000 down in the bottom corner. It doesn't matter what number you start with. I could have started with 100, but when they give me things like 5.4% or something like that, right? Like that's not going to go into 100 very well because that would literally be 5.4 people. So I usually start with a really big number like 100,000, okay? All right, we know that the probability of getting cancer is 1%, 1% chance of cancer. That means cancer total all the way across here. My total number of cancer people is 1%. If I have 100,000 people, how many is that? 1,000, right? 1,000 people have cancer. Now I can fill some of the other parts of this table in. If 1,000 people out of 100, this would be 99,000, right?
Yep.
So this reflects a 1% cancer, right? 1% out of 100,000. Again, I made that 100,000 up, but it doesn't matter what it is as long as it's reflecting the percentages accurately, right? Okay. Now the next thing says a false positive. We've already identified the false positive. False positive is 10%. False positive. This happens 10% of the time. 90% of the time they are identified accurately as negative for cancer. But a false positive occurs 10% of the time. What do I take 10% of? 99,000. What's 10% of 99,000? Move the decimal.
9,900.
9,900, right? Move the decimal over. 10%, okay? 90% would be the remainder of that. So like 89,100. I don't know if I did that right. Check me.
What do you want?
89,100 plus 999.
89,100.
Is it 89,100? Okay, so I can get those numbers that way, right? Okay, now a true positive rate A true positive rate is 80%. Where are my true positive people?
Positive test result.
Positive and cancer. These are true positives right here. And this happens 80% of the time,
800.
which means 20% of the time we're getting false negatives, correct?
Correct.
Okay, now 80% of 1,000 is 800. 20% of 1,000 is 200. So they add up to be like that, right? These are the numbers that we have from this table. Does that make sense?
Yep.
Okay, now our last question is find the probability of, what does C mean? Cancer.
Given.
Cancer given positive. Okay, so find the probability of cancer given positive. Probability of cancer given positive. I'm writing it down here so you can see it. Find the probability of cancer given positive. Okay, so I'm looking only at the positive people. Only the positive people. How many positive people do I have total? Positivers. Positive testers.
Shoot.
How many positive testers do I have?
10,700.
10,700, right? Those together. Of those 10,700, how many had cancer?
800.
800, okay?
0.0748.
0.0748. Okay? Now, 7%, right? Like 7.4%. These are the people who have cancer that tested positive. Okay, now let's talk about what this means. Okay, are you ready? We don't have a test that's completely 100% accurate, right? Like if you go in and you get tested for cancer, you could have some blood condition and it flag the system and say you have cancer, but you actually don't have cancer. So here's the deal. We are testing, and out of all of the people who test positive for cancer, all of the people who test positive, how many people or what percent actually have cancer? 7%. That means 93% of all of the people who are testing positive for cancer actually don't have it. That seems like crazy to me, but that's what this data is reflecting, because our tests are only like, what, 80% accurate or whatever it was?
Is this a real
Only 7% of the people. I don't know. It's probably a little bit better than that. Like our tests are probably better than 80%, but it still reflects that. Like still nowadays, the majority of people who test positive for cancer actually don't have it. Like if they run a blood test. Now, most of the time cancer is identified from like a biopsy of like a tumor or something, but if they just test your blood and say you have cancer, 93% according to this don't actually have cancer according to their blood. That just seems like crazy to me, right? But that's what this is saying right here. That's what it's saying. That's what the data suggests. Okay? Good? All right, you guys don't have that. Is that the end of the notes?
Yeah.
Yay! Okay,
Okay, we have a question.
that's all.
We have a question.
What?
I don't know how to do 11. And that's
Okay, I'm gonna pause the video. Bye, Kelsey.